Hi all, and welcome to the section 4.3 video lecture on monotonic functions and the first derivative test. So a function that is increasing or decreasing on an interval is said to be monotonic on the interval. So suppose that f is continuous on a comma b and differentiable on a comma b. If f prime of x is greater than 0 at each point on x in a comma b, then f is increasing on a comma b. And if f prime of x is less than 0 on each point in x in a comma b, then f is decreasing on a comma b. So the idea here is if the derivatives of at every point in an interval are positive, therefore the tangent line has a positive slope, then we say the function is increasing. And likewise, if all of the slopes are negative, we call the graph decreasing on that interval. So suppose that c is a critical point of a continuous function f, and that f is differentiable at every point in some interval containing c, except possibly at c itself, moving across the interval from left to right. If f prime changes from negative to positive at c, then f has a local minimum at c. If f prime changes from positive to negative at c, then f has a local maximum at c. And if f prime does not change sign at c, that is, f prime is positive on both sides of c or negative on both sides of c, then f has no local extreme value at c. So if we go from negative to positive, that means we had a negative slope, so the graph is going down, and then we get a positive slope, so the graph is now going up. That means that point where that change signs is where we had a minimum value. And if we have the opposite of true, then that means the graph is going up, but then it starts going down. That means we get to the top of the hill, we go over the top of the hill, and we go back down. So that top is the local maximum. And if we go up to our critical point and then continue up, basically what happened is the graph just flattened out for a moment. So it's like if we're walking up the hill and we get to a flat part, but then we continued to go up. We haven't reached the local top of the hill yet. Therefore, what we want to look at is we like to, in order to find all the local extreme values and increasing and decreasing, then what we can do is we can find the first derivative. So for example, in this function here, if I take the first derivative, so g prime of x is 4x cubed minus 12x squared plus 8x. And what we want to do is we want to set that equal to 0. So that's 4x cubed minus 12x squared plus 8x equals 0. We can factor out a 4x, which leaves us with x squared minus 3x plus 2 equals 0. And then we can factor that. So that's 4x times x minus 2 times x minus 1 equals 0. And so we get x equals 0, x equals 1, and x equals 2. Okay, so those are all our critical points for this. So now to figure out whether or not where this is increasing, decreasing, and constant, what we need to know is we need to know what is the value, what is the sign of the function in each one of those intervals. So what we could do is we could make what's called a sine graph of this. So what we have is we have our x values here, and then above it we have the sine of g prime of x. Okay, so we've got our x values at 0, 1, and 2. And now to find the sign in each one of those, we plug a number in each one of these intervals into that function. So for example, I could find g of negative 1. I could g prime, of negative 1. G prime of 1/2. G prime of 3/2. And g prime of 3. So these are all places where the function is 0. And then all these numbers are in these intervals. So negative 1's right there, 1/2's right here, 3/2 is in this interval, and 3 is over here. Okay, so we plug those values in. So we'd have 4 times negative 1 cubed minus 12 times negative 1 squared plus 8 times negative 1. And we'd have 4 times 1/2 cubed minus 12 times 1/2 squared plus 8 times 1/2. And we'd have 4 times 3/2 cubed minus 12 times 3/2 plus 8 times 3/2. And finally, we'd have 4 times 3 cubed minus 12 times 3 squared plus 8 times 3. Okay, and so what we want to do is we want to plug each one of those into our calculator and see what we get for values. Okay, and so okay, so for the first one, we get negative 24. For the second one, we get 1.5. For the third one, we get negative 1.5. And for the last one, we get 24. So for this graph, it's negative over here to the left of 0, positive between 0 and 1, negative between 1 and 2, and positive to the right of 2. So this graph is decreasing from negative infinity to 0 and from 1 to 2 because we have a negative sign on the derivative. It's increasing from 0 to 1 and 2 to infinity because we have a positive sign on the derivative. And then at our different zeros, we can decide if those are mins or maximums. So it's a minimum if it goes from negative to positive. So here it goes from negative to positive, right? It's negative to the left of 0 and positive to the right of 0. So we're going to have a minimum value at 0. And another place we're going to have a negative minimum at is at 2 because it goes from negative to positive. But then at 1, it goes from positive to negative. So that's going to be a local maximum. Okay, so that's the idea here. Now, one of the things you can try and do with this stuff is you can try and use the Class Calc app to help you find these. Because obviously, all of this stuff is stuff that's talking about what the graph of the function looks like. So if we open the Class Calc app on our calculators and we graph the next function, which was, wrong app, which was x squared times the square root of 5 minus x. So we're going to graph y equals x squared times the square root of 5 minus x. Okay, we can, and if I zoom out a little here, Okay, we can see that this graph has two critical points at 0, 0 and at 4, 16. Okay, and we can also see the intervals on which this is increasing, decreasing, or constant. So if we look at this, we can see that the graph is over here on the left is decreasing, right? Because the graph's going down. Then it goes up between the two, and then it goes decreasing again. And then the other thing we should notice here is this graph stops at 5. Because if I plug in any number that is greater than 5, I'm going to get undefined. Okay? So we can go back here. And if we wanted to, we could draw this graph in our notes. Okay, so we've got this graph looks something like this. It comes down till we get to 0, 0, then it goes up to 4, 16, and then it stops right there. So we've got 0, 0, 4, 16, and this last point where it stops should be at 5, 0. Yeah. So the last point is at 5, 0. So from the graph, we can also get a lot of these things. And if we wanted to, we could also check them then using our derivatives. But if we look at this, we can see that the graph is decreasing on this interval on the left. So that's from negative infinity until we get to 0. Then it's also decreasing from 4 to 5. And it's increasing from 0 to 4. We can also see that there is a local minimum at 0, 0 and at 5, 0, and a local maximum at 4, 16. Okay, and so all of that came from the graph. So we should be able to do this both ways. In fact, most of the time it's going to be easier to do it by looking at the graph, but that may not always be an option we have, depending on what types of values we're looking at. So for example, we could try the second one here. So if I graph that one, so x cubed divided by 3x squared minus 1. Okay, and so let's zoom in closer here in the middle. Okay, and if we look, this is another one where we can easily do this simply using the graphing calculator. So if without having to necessarily do this by hand. So if we look at this graph, right, we can see these different points. So I could transfer this onto my note sheets if I wanted to. So in our notes, this would look like this. So we've got our axes. Okay, and so we've got a piece of the graph that goes like this. And then we've got a piece of the graph that goes like this. And then we had a piece of the graph that goes like this. Okay, and this point had a maximum over here at 1, negative 1, negative 1/2. We had a critical point at 0, 0, and we had a local minimum at 1, 1/2. Okay, so from this graph, and then also one of the things that may not be clear is what's happening where these asymptotes are. Okay, and those asymptotes happen when the denominator is undefined. So we may need to use some algebra there to find out when those points happen. And there's a couple, the easiest way to go about that is to just figure out from the function itself when that is. So those are going to happen when this function is undefined. So that's at 3x squared plus 1 equals 0. Oh, sorry, this graph is very incorrect because I drew the wrong function. I used a minus plus 1 when I should have used a minus 1. So let's go back. Let's try this one more time. So I did not do that correctly. Sorry. This should be a plus 1. Okay, so we get a very different graph, which is a useful thing to notice here. So if we look at this one, in this case, we actually only get one critical value at 0, 0. So that's going to give us a very different answer than the one that I just showed you. So if we look at this graph actually looks like this, right? It's just a line that comes up here and then it flattens out and then it goes on. And that happens at 0, 0. Okay? And so what should happen if we use the derivative test here is that we should get that this graph increases from negative infinity to 0 and then from 0 to infinity. And we shouldn't get any local maximums or local minimums. So we could go ahead and try that out here if we wanted to. So if we found the derivative of this, so f prime of x is going to be the bottom times the derivative of the top, right, minus the top times the derivative of the bottom over the bottom squared. So that's f prime of x equals 3x squared plus 1 times 3x squared minus 3x squared times 3x squared plus, oh, what? Nope, sorry. X cubed times 6x. Okay? All over 3x squared plus 1 squared. So then, if we multiply these out, we get 6x to the fourth plus 3x squared minus 6x to the fourth over 3x squared plus 1 squared. And then f prime of x equals, these cancel, so we get 3x squared over 3x squared plus 1 squared. Okay, so now that we've done that, we can see that this thing's only going to equal 0 when the top equals 0. So the function will, f prime of x will be 0 at x equals 0. And so what we want to do is we can make our sine graph. So we've got only one critical point at 0. This function is 0. And so then we can plug in values for x on either side. So I want to find f prime of -1. So if we do that, it's -1 up here, so it's -3 over, it's +3 over, this would be 3 plus 1, which is 4, squared is 3 over 16. And then if we do the same thing for +1, we get 3 over 16. So this is positive on both sides. And so as we can see, that means we get no minimums or maximums because the sign did not change of the derivative on either side of that critical point. Okay, so all we end up with is this increasing it in that interval. Okay, so what I'd like you all to do is take a moment or two, pause the video, and try doing these other two. Feel free to try out both methods. I'd like you to try doing one of these with the derivative, and you can also do it with graphing. It's also a good way to check your answer. When we come back, we're just going to do them both with our derivative. So go ahead and pause the video and give these a try. Okay, so now that we've got these done, that you've tried these, let's just run through the answers real quick, right? So the first step is find the derivative. So this one would be 6x squared minus 18. Then set that equal to 0. And this is actually going to end up being an example of one where you cannot do it by graphing. Because if you try to do it by graphing, divide by 6. If you try to do it by graphing, what's going to happen is you get an irrational answer. So this is x squared equals 3, so x equals plus or minus the square root of 3. Okay, so our critical values are not happening at whole numbers or decimals, so we're going to have to do this one by hand. So in this case, I've got my 0 here, and then I've got negative root 3 and positive root 3. And my zeros are happening at negative root 3 and positive root 3. And then what I want to do is I also want to pick some other values that fall into these other two intervals on the outside. So 2 is greater than root 3 and negative 2 is less than root 3. So we could try those as well. So now we plug in f prime of negative 2, f prime of 0, and f prime of 2. So plug those numbers into f prime. So that's 6 times negative 2 squared minus 18. 6 times 0 squared minus 18, and 6 times 2 squared minus 18. So 6 times 2 squared, so 4. That's 24 minus 18 is 6. This one would be negative 18, and this one's also positive 6. So we go from positive to positive. So our function is increasing from negative infinity to negative root 3, and from root 3 to infinity, because the sign on the derivative is positive, so the function's increasing on those intervals. Then it's decreasing between where the sign on the derivative is negative, so that's between negative root 3 and root 3. And then we can see we have a maximum at negative root 3 because we go from positive to negative, and we have a minimum at positive root 3 because we go from negative to positive. Okay, so that's all there is to that. Okay, so let's try one more together. We'll just run through the answer of this other one real quick using this first derivative test. So the first derivative of k is 45t squared minus 5t to the fourth. Set that equal to 0. So 45t squared minus 5t to the fourth equals 0. We can factor out a 5t squared times 9 minus t squared. So that equals 0. So this first, you set them both equal to 0. So solve this one and you're going to get t equals 0. Solve this one and you're going to get t equals plus or minus 3. So this is one you could have done with your calculator because all of those are whole numbers. So if you had graphed this original function, you would have been able to see where the minimums and the maximums were. So you wouldn't even need to do this first derivative test at all for this one if you didn't want to. So we can make our sine graph now. So we've got negative 3, 0, and positive 3, and we want to pick a number in each one of those intervals. So I'm going to use negative 4, negative 1, 1, and 4. And you could pick any number that falls into those intervals. Okay, so now we find k prime of negative 4, k prime of negative 1, k prime of 1, and k prime of 4. Okay, so if we do that, we get 15 times negative 4 to the third minus negative 4 to the fifth. Sorry, I'm doing the wrong equation. 45 times negative 4 to the second minus 5 times negative 4 to the fourth. Okay, so that's negative 560. And I believe if we put that into the other one, into it when we get a positive 4, that we should also get negative 560 because we're dealing with even exponents. So we should get the same answer whether we're putting in the negative or the positive of the number. And if I plug in 1, if I plug in -1 or 1, I get positive 40. So in this case, I get 0 at -3, 0, and 3. To the left of -3, I'm going to get negative results. Here, I get a positive, positive, and then negative. Okay, so in this case, we can see that this function is increasing from -3 to 0, and from 0 to 3. It's decreasing from -infinity to -3, and from 3 to infinity. And last but not least, we can do maximum. This has a maximum at +3 because it goes from positive to negative, and a minimum at -3 because it goes from negative to positive, and there is no minimum or maximum at 0 because it stays positive. So there is no minimum or maximum at 0. So that's the idea. Okay. Okay, so the rest of these functions are the same idea, except we're trying to decide if values are absolute. So the reason, so the only way for a function to be an absolute is if the local extreme is if it's a local extreme value and the function in no other place gets larger or smaller than that. So for example, if we try to do this first problem by hand, okay, we're only looking in this interval, but we need to find the derivative like normal. So g prime of x equals, and now I'm going to have to do the quotient rule. So the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Okay, so that's 4 minus x squared times 2x minus x squared times -2x all over 4 minus x squared squared. And then g prime of x equals 8x minus 2x cubed plus 2x cubed over 4 minus x squared squared. And if we simplify, we get g prime of x equals 8x over 4 minus x squared squared. Okay, and now that we've done that, we can set that equal to 0, and the only solution is going to come from the top, right? Because if the bottom's 0, then the whole thing's undefined. So we can set 8x equal to 0, so x equals 0. So now what we have is we have our endpoints, and we have our critical values. Now, notice I only actually have one endpoint here because we're not equal to -2, but we could see what the value is doing over there to give us an idea of what we're looking for absolute maximums and minimums. So what I want to do is I'm going to put in, actually -2 is not going to be that useful to us. Actually, either there's a typo here or these are the only values we want to look for. So there are no critical points in this interval because -0 does not fit in there. So what I'm going to do is I'm going to test -1, and then I'm going to pick another number in this interval. So let's say, let's actually, instead of using, instead of finding, I think this is actually a typo. So let's go and change this -1 to a 0. So now let's find x and g of x, and let's plug in. What we want to plug in is we want to plug in the endpoints and our extreme value. and then we can work from there. And the nice thing about this is these work as if they're numbers on either side of 0. Now, in this case, if I try to plug in -2, I'm actually going to get undefined, right? Because the bottom's going to be 0. So that would be undefined. So I'm going to want to pick a number that is between 0 and -2. So let's try -1, 0, and 1. So if we plug those into the original function, we can find these values and decide if they're absolute or not. So if I plug in -1, I get 1 over 3. So I get 1/3. If we plug in 0, I get 0. And if I plug in 1, I get 1/3. So what we can tell from this is that, first of all, 0 is definitely a minimum, a local minimum, and 1 is definitely going to be a maximum. And in this case, what I can tell is this one, 0, 0, is an absolute minimum in this interval, because no value in this interval gets any smaller than -1. Than 0, 0. However, 1 1/3 is not an absolute maximum, because these values are going to continue to increase on the other side, and therefore this would not be an absolute maximum. So if I graph this, so let's graph x squared divided by 4 minus x squared. And if we set the domain to match what we said it was, so we can set the domain by holding down on this purple circle, and it'll give us that option, right, of setting domain. So I put in -2 to 1. And if we now look at this graph, we can see that 0, 0 is definitely a absolute maximum. It is the lowest the graph goes in this interval, but 1, 1/2 is not. 1/3 is not, because this side of the graph goes up much higher than that value. And that's exactly what we found algebraically. Okay, so that's the idea. So we're looking at the same idea here. We're just limiting it to the regions we're looking at. Okay, so let's go ahead and try another one of these together. So we can start by finding the derivative. So in this case, I'm going to have to do the chain rule. So the derivative of square root is 2 over the square root of x squared minus 2x minus 3. Okay, and then we can, that's going to be times the derivative of the inside, so x squared minus 2x minus 3. And so f prime of x is going to be the derivative of this on top of here. So 2x minus 2 over 2 times the square root of x squared minus 2x minus 3, and then we can cancel out a 2. So f prime of x equals x minus 1 over the square root of x squared minus 2x minus 3. Okay. And so now, if we solve this, we should see that the only critical value that's going to happen here is at when the top equals 0, so x minus 1 equals 0, so that's going to happen at 1. Now, is 1 in our interval? Well, the answer is no, right? 1 is not in our interval. So that means all we have to really look at here are, we can look at our endpoint, which is 3, and we probably want to pick some number larger than 3 so we can see if it's going up or down. And because there are no critical values in this interval, we know that this 3 will either be an absolute maximum or an absolute minimum. This graph is either going to go up from 3 or down from 3. It's never going to go change directions because we don't have any critical values in the interval. So if we do this, so if we plug in 3, we get 9 minus 6 minus 3, which is 0, so I get 3 comma 0. And if we pick a number larger than 3, like let's just say we plug in 4, then we get 16 minus 8, which is 8, minus 3 is 5, so we get the square root of 5. So we can tell that this is going up forever from 3 comma 0, so that makes this an absolute maximum. And once again, we can check the graph to see if that's actually the case. So I'm going to graph the square root, y equals the square root of x squared minus 2x minus 3. Whoops, sorry, I hit the wrong. Minus 3. Okay. Whoops. 2x minus 3. And so if we go over, and I'm going to set the domain. So I hold down on that circle, hit set domain, and I want to go from 3 to infinity. So I'll just put a 3 on the right. And so now we're going to need to come over to here, and we can see from the graph that this starts at 0, 3 and goes up forever without bound. Okay, so that's the idea. So why don't you all take a moment, pause this video, and try the next couple problems on your own. And when you come back, we'll go through them. Okay, so same idea as before. Start by taking the derivative. So in this case, it'll be negative 2x minus 6. Set that equal to 0. Okay, and so we get add 6 to both sides, divide by negative 2, and we get negative 3. So now we want to check x and g of x at our endpoints. So in this case, negative 4 is the only endpoint at our critical values. And then you also want to pick a value that is larger than negative 3 so you can tell whether or not the graph goes up or down from there. So let's pick 0, for example. So plug those into the function. So if we plug in negative 4, we get negative 16 plus 24, which is 40 minus 9, which is 31. If we plug in negative 3, we get negative 9 plus 18 minus 9, which is 0. And if we plug in 0, we get negative 9. Oh, sorry, I did this negative 4. I don't think I have correct. So that should be 16 negative 16 plus 24, which is negative 16 plus 24, which is 8 minus 9, which is negative 1. Okay, so that makes more sense. So in this case, what we can see is that negative 4 is a minimum, okay, because it is an endpoint that is smaller than the stuff to its right. Negative 3 is actually going to be an absolute maximum because all the values are less than it. And then there is no absolute minimum because the stuff to the right of negative 3, 0, negative 9, is actually more negative than this local minimum can be. And then we could look at the graph and it will confirm that. And then we could try one more here. So we start by finding k prime of x. So that's 3x squared plus 6x plus 3. Set that equal to 0 and solved. And we get, we can divide by 3, so it's x squared plus 2x plus 1. We can factor that as x plus 1 squared, and so we get x equals negative 1. And then we can do the same basic idea we did up here. We do the endpoint, which is 0. We do our critical value, which is negative 1, and then I pick some value that is on the other side of our critical value from our endpoint, so like negative 2. So if I plug in 0, I get 1. If I plug in negative 1, I get negative 1 plus 3, so negative 1 and the negative 1, so I'm going to get 0. And then if I plug in negative 2, I get negative 8 plus 12, which is 4, plus negative 6, which is negative 2, plus 1, which is negative 1. Okay? And so in this case, what we should notice is this 0, 1 is actually going to be an absolute maximum because everything is smaller than it. And there is no minimum because notice this goes from a positive to a negative on the other side. So this does not turn around at that point. And we could check that by looking at the derivative. If I plug in this derivative is always going to stay positive. And if I look at the graph of this one, so y equals x cubed plus 3x squared plus 3x plus 1. And if I set the domain so that it's negative infinity to 0, like in the problem, we can see that at 0, we get an absolute maximum, but at negative 1, it's not a maximum or a minimum. And so that's the idea. Okay, and then beyond that, we could also do this same kind of thing with trig values, okay, if we wanted to. So I would highly, yeah, so it would be the same idea as what we just did, just doing with trig values. So let's go ahead and do at least one of those. So start by finding the first derivative. Right, so in this case, that would be negative 2 plus so that's secant squared x. And then we can solve, set that equal to 0. Add 2 to both sides. So we get 2. And then we can take the square root of 2. So that's plus or minus the square root of 2. And then we want to know when is secant equal to plus or minus the square root of 2. So we could actually do that with our graphing calculators if we wanted to, especially if you have your graphing calculator in degrees. So if I go to my ClassCalc app, let's go to the scientific calculator, and I can do inverse secant. Hopefully. Okay, there it worked. Okay, inverse secant of the square root of 2. And it tells me that's 45 degrees. So that's a pi over 4. And then I can also do the negative square root of 2. And it tells me that's 135, which is 3 pi over 4. So when we go back here, we get x equals pi over 4 or 3 pi over 4. And only one of those is in our interval, which is, okay, so in our only one of those is in our interval. 3 pi over, no, yeah, only one of those is in our interval. 3 pi over 4 is not, so we don't have to worry about that one. So now we do the same thing we did on the last page. We're going to plug those and our endpoints. Although in this case our endpoints are not included, so don't do your endpoints. So what we're going to do is we're going to just look at, we can just use the second derivative test here, right? So what I want to do is I just want to plug in numbers smaller and larger than this into secant squared. Negative 2 minus secant squared. So if I, yeah, so I've got my line here. I've got pi over 4. I've got, which is a 0. I've got pi over 2, which I don't want to plug in because it's not included. I've got negative pi over 2 over here. And I just want to pick some values that fit into those intervals. So I got 0 would be a good one to plug in. And we could also plug in pi over 3. Okay, so f prime of 0 and f prime of pi over 3. So f prime of 0 is -2 plus secant squared of 0. Secant squared of 0 is 1 over cosine of 0, so that's 1. So this would be -1. And then if I plug in pi over 3, so pi over 3, the cosine of pi over 3 is, well, here, I'll just, the easiest way to do this is plug it in your calculator. So if we do it in our calculator in radians, I want to do -2 plus secant of pi divided by 3 squared. And if we do that, we see that we get the answer 2. Okay. So that means it's positive over here and negative over here. And there are no other critical values. So whatever this is, it will be an absolute value for that one. And so in this case, the local extreme value is at pi over 4. And it should be a it goes from negative to positive, so this is a local minimum because we go from negative to positive. Okay, and so that's the idea. Okay, so this is probably a long enough video already, so I'm going to leave it to you guys to practice these other trig functions in the homework. And if you have any questions, don't forget about my virtual office hours, which I'll try and have a few each week and let you know when they are by email. Or you can always call, text, or email any questions you have.